So, this lecture we will focus on the stationary process, we will discuss about the response spectrum. This is lecture 2 on module 3 on dynamics of motion structures under the brace of NPTEL IIT Madras. In the last lecture we discussed about stochastic process. In this lecture we talk about something called stationary process. Then for a stationary process we will derive the equation for response function or a transfer function. Now in most of the cases in offshore structures, the environmental loads which act on the system are actually a stationary process. Now the question comes, what do we understand by a stationary process? So look at these values which are x1 of t, x2 of t and xn of t. So stationary process is that process where the mean standard deviation of these variables are independent of time and position. So literally for a stationary process, if these two conditions are satisfied, then what are the advantages of a stationary process? If you know the advantages, then from the advantages we will try to derive the transfer function between the response and the load. Now let us see what is our objective. I have a system structure, the system is subjected to some load and the system responds. Now my objective is to obtain a transfer function which gives me the mapping of, for a given load, what is the response. That is my objective actually, is it not? In the whole analysis, that is my objective. I must have a transfer function which understands or gives me a mapping of the load onto a structure which gives me a response for a specific load, right. If the system what we are talking about here is stationary, then the transfer between the load and the response the transfer between the load and the response can be modeled as linear time independent or time, let us say, invariant, does not vary with time system. This can be characterized by a transfer function. So, our objective is to derive a transfer function which gives me the connectivity between the load acting on the system and the response received by the system because of the load acting on it. Okay. Fortunately, if the system qualifies to be called as a stationary process, then I can characterize this transfer function as a time invariant problem. Okay. Any questions here? So, now the question which I got to answer is, or verification which I got to do, are the following. What are the verifications we have got to do? The verifications are the mean value of the variable, which is expected value of x of t, should remain as constant. That is, we have got to verify this, because then only we can call this process a stationary process. Or to be more elaborate, mx is mx of t is constant, I mean time invariant, and the autocorrelation function which is expressed as r x of tau, which is given by expected value of x of t and the product of x of t plus tau, should remain as function of tau only, not t. To be very specific, I have got to verify the following. 1, my mean, which is nothing but 1 by n of sum of j is equal to 1 to n of xj of t, and my autocorrelation function, which is a function of t and t plus tau, which is given by 1 by n of sum of xj of t, xj of t plus tau, should remain independent of time. So, for a given process, I must evaluate the mean and autocorrelation function. I must show that they are independent of time. Okay. So, for that process, I expand and get a relationship between the loading function and the response function. I call that function as a transfer function. Okay. Then leading to that, we will get into response spectrum. Any questions here? I think I will use this side, it is easy. Is there any problem? Are you able to see from here? Now, if these values, that is mx and rx tau of t, remain independent of time, then we can say that mx, expected value of x of t, remains as constant, and the auto covariance function which is given by Cx of tau, which is expected value of mx minus x of t minus mx, product of x of t plus tau minus mx remains as function of tau only, not t. So, the advantage is, now for a given load which varies, I get a variance spectrum. For a given structure, it has got a response, the response varies, I get response spectrum. Connecting these two is my transfer function. So, I am interested to derive the transfer function in the process of showing that the process is stationary. So, I must establish these two conditions, show the process stationary. For that process, I want to connect the variance spectrum of the load to that of the response. I get the transfer function. The moment I get the transfer function, I can find the response spectrum if I know the load variance spectrum. Okay. Any questions here? Remove this. We have already seen the stochastic process in the last lecture yesterday, that stochastic process leaves a realization of the value of the variable. For example, for each realization small f of t of f of t, small f of t or realization of f of t, capital F of t is a large ensemble, out of which small f of t, f1, f2, f3 are all realization values of this f of t. Okay, these are all true values present in that set. We get the corresponding realization x of t of x of t. Is that okay? These are all responses. Hence, x of t, which is a realized value, can be given as integral of domains minus to plus infinity h f x s, I will come to that what it is, f t minus s ds, where h f x s is called the impulse response function. What does it mean? For any force, if we know what is the impulse of that force caused on the response, because these are all realization of the force, f of small f of t are all realization of the force. Okay? If I know how much realization is being impulsed upon by this factor, I will know the realization of x for a corresponding value of the force multiplied by that response from a domain of minus to plus. You will always agree that impulse response function in a negative domain is always 0, because it is giving a positive impulse only. So, I can rewrite this equation as 0 to infinity h of fx, this is capital X, yes, f of t minus s ds, since h of fx is 0 for s less than or equal to 0. So let us say less than 0, because at 0 you have value, you do not know. Let us call this equation number 1. So this is my x of t. I am getting the response realization for a force realization multiplied by the impulse response function of that. Okay. Any questions here? We will remove this. Having said this, we can establish the capital X t values, because we are talking about the x of t value for a whole domain of 0 to infinity. I can establish the x of t as also similar to 0 to infinity h of fx of s with capital F of t minus s ds. Okay. These are all nothing but the space of x and capital F. The earlier expression 1, equation 1 was giving you only the realized values within this space. So I can call this equation number 2. I can say equation 2 interprets that there is a corresponding pair between x of t and f of t minus s, or x of t and f of t for the whole domain 0 to infinity. There is a complete connectivity between these two. Okay. So they are connected. So x of t and f of t are connected. Okay, that is the mathematical meaning of this expression, is it not? So that connectivity is what we are trying to establish. Interestingly, the impulse response function which is h fx of s is also called as transfer function, because it establishes the connection between load and the response, is it not? The load, the response. I can always call this as response function also. Please note that the impulse response function is independent of time. Okay, there is no time factor here, it is independent of time. Now you may wonder that in h fx of t, s is a variable or t can also be. You can wonder that yes, since t is there, x of t is there, is it a function of time? It is not. The fx term is indicating h fx indicates that the connectivity is between f and x. For example, if I have, for example, if y of t is the load process and okay, y of t is the response, sorry, is the response for the load process g of t, then the transfer function can be indicated as, not given by, can be indicated as h of g y of t, which is as same as h of f x of t. So, the first letter here stands for load, the second letter here stands for response. So, our job is to estimate this transfer function now. Because if you know the transfer function, I can easily find the response if you know the load spectrum. Okay? Can I remove this? So, let us say x1 of t, x2 of t, xn of t are realizations of x of t, and f1 of t, f2 of t with fn of t are realization of f of t. Then I can say 1 by n of j equals 1 to n of xj of t is 1 by n of integral j equals 1 to n of summation of integral of my transfer function 0 to infinity h of x of s fj of t minus s ds. I call this equation number 3. This is what I have borrowed from my response, is it not? I am using the response as a transfer function or impulse response function on the load. I am using all small because I am talking about realization for an entire domain of 0 to infinity, which can be rewritten as where there is no time component here, h of fxs, the integral domain is there for the entire domain, and then the summation of 1 by n of j equals 1 to n of fj t minus s ds. Equation 4. Therefore, what is this value? This expected value of, what is this value? It is mean of the response function, is it not? Which is now given as limit n tends to 0, sorry, infinity, n tends to infinity 1 by n of summation of j equals 1 to n of xj of t, which I am rewriting from here, which is given as for the integral of the transfer function 0 to infinity h of xs summation 1 by n of j 1 to n of fj of t minus s of ts, which can be said as, what is this value? Yeah, expected value of this variable, is it not? So I can rewrite this as, I am writing it here, I will remove it. So I can rewrite this as integral of 0 to infinity h of xs expected value of f of t minus s ds. Is that okay? Now we already know, I will call this as equation number 6. Okay, this was 5. Now we already know that if f of t is a stationary process, which in most of the cases in offshore structures is true, then we have a very important interpretation. Then I will remove this. The mean value of this, which is m of f, I am talking about the load, the mean value of this, which is expected value of f of t, is constant, is it not? That is the definition for a stationary process. Therefore, E of x of t, which you have here in the previous equation, can be rewritten as, this can be written as a constant. Instead of using a constant as k etc., I am using as mf. Okay, I am taking this outside the integral, I am simply saying h of x. Is that okay? ds, integrals over the domain. I call this equation number 7. Now interestingly, the expected value of the space of x of t is independent of time. Okay, so you can see here equation 7 is independent of time, which confirms that it is a stationary process. Okay, any questions here? Now my focus is to evaluate this. Any questions? I will remove this. Having said this, now let us say capital H, because we are talking about the transfer function for realized values of f on realized values of x, which are true for the entire domain of 0 to infinity. Now I am talking about the transfer function for the whole domain as a capital H now. So capital H f of x omega be a transfer function that corresponds to the impulse response function h of fx of t. Then we can say that h fx of 0 is straight away 0 to omega infinity h f x s ds. Equation number 8. Now I have the equation 7. I am rewriting equation 7 as the original equation 7 was this: E of expected value of x of t was given as the mean value of the force of 0 to infinity h of x of s ds. Is that okay? This was the original equation 7 we had. I rewrite this as rewritten as expected value of x of t as mf. Instead of this I am using this, so h f x 0. I call this as mx. So I can say mx is nothing but mf of h of fx of 0. Equation number 9. So if I know the mean value of the forcing function or the process, can always find the mean value of the response function when I know the transfer function. In stochastic process we will not get the absolute values of x, we will get only the statistical parameters of x like mean, standard deviation and coefficient of variation. So I can get this if I know this. So my objective is for a given problem how to get this value. Agreed? And there is no time dependency here, therefore the process is completely stationary. Okay. Now we will take up a single degree freedom system example. Try to connect what is the connectivity this function has with the problem. So I will remove this now. Any questions here? So what we picked up, to be very brief, you can turn back and see, we started with the stationary process explanation. We wanted to emphasize that stationary process is that process where the mean and standard deviation are independent of time and space or position. Okay. So we said two values are got to be qualified, one is the mean should be constant and second is the autocorrelation function should remain independent of time. Okay. We picked up that then if a process is said to be stationary, the load acting on the system which is the process said to be stationary, then there exists strong connectivity between the load acting on the system with the response given by the system onto the load. Okay. So I can easily find out this mapping using a function what I call impulse response function or a transfer function. So for a stationary process this should remain independent of time again. Okay. So we showed that small h of x of s is independent of time, right. We picked up that now we connected the mean of response to that of mean of forcing function with this value. So now we will apply this concept back again in a simple problem and derive the transfer function for that problem. Okay. Let us pick up a single degree freedom system problem quickly with a damped system and see how I can derive the transfer function for that particular problem, then from that problem how do I get the response spectrum. So I have a single degree freedom system problem. Yeah, K C x of t f of t. So we already know mx double dot plus Ex dot plus Kx is f of t. In my case I take this value as P0 some harmonic function. So, the steady state response, referring back to the lectures on module 1 of, I am using P here to indicate it is a particular integral. Okay. There are two solutions for this differential equation. One is the complementary function, as the particular integral. Complementary function is closely related to my transient vibration. I am dying down, I take only the steady state response, which is assumed as let B1 cos omega t plus B2 sin omega t. We have already known that the response of my steady state will have a functional component of the forcing function. Okay. So, can we quickly find out x dot and x double dot, substitute these values in this original equation, can you get me B1 and B2 quickly? So, you have to simply differentiate it once and twice, substitute these values back and get the values of B1 and B2 quick. So, minus B1 omega sin omega t plus B2 omega cos omega t minus B1 omega square cos omega t minus B2 omega square sin omega t. Substituting back, m of minus B1 omega square cos omega t B2 omega square sin omega t plus C of minus B1 omega sin omega t plus B2 omega cos omega t plus K of B1 cos omega t plus B2 sin omega t is P naught cos omega t. Now, I pick up the terms associated to cos, associated to sin separately, two equations, get B0, B1 and B2 quickly. So, if you look at the cos terms, terms associated with cos omega t, both LHS and RHS. So, I can say K minus omega square m of B1 plus omega c of B2 is P naught minus omega c of B1 plus K minus omega square m of B2 is 0. Is that okay? All right. So, write in matrix form, invert it and get B1 and B2. I can write this as K minus omega square m omega c minus omega c K minus omega square m of B1 B2 is P naught 0. So, B1 B2 is nothing but inverse of this matrix of P0. Okay. Okay. Now, for beta to be a ratio of omega by omega n, it is a frequency ratio, and zeta be the damping ratio, we already know the dynamic amplification factor D for this problem is given by, can you give me what is that equation for D, if you remember? I will write down here, I have the equation here. Can you, if you have the notes earlier, can you just tell me what is the equation of D? Good. So 1 upon square root of 1 minus beta square the whole square plus 2 zeta beta the whole square. Is it okay? And what is the upper limit of this for a weakly damped system? The upper limit. So I should say, let us say for a weakly damped system, D is approximately given by 1 by 2 zeta. What does it mean? If I have zeta as 2%, the magnification will be 50 times. So if we have a zeta of just 2% in a given system, the maximum amplification what I will get for the system will be about 25 times, isn't it? Okay, that is the meaning physically. What does it mean? Even for a small oscillation, the magnification is very high. The damping 2% means small oscillations, isn't it? It is not damping at all, it is not dying down. So then I can say, remove this, then H of omega multiplied by P naught of cos omega t minus phi can be said as x of t. Is it okay? H omega is nothing but the function on P naught. What does it mean? It is nothing but the amplification of P naught on the system. So H omega, this is equation number 12. I mean, my numbers are continuing. I am getting equation number 12 here. 11 somewhere down the line, D was 11 I think. So H omega gives me the amplitude amplification. What is going to be amplitude? P0 is my amplitude, okay. You see the forcing function, it is P0 cos omega t. So P0 is the amplitude of the forcing function. Amplification is this content, magnification, and phi gives me the phase lag. Okay. Now for H omega as 0.001, the amplification is so small, 0.1%, okay, 0.001 at a specific frequency, at any frequency omega, and P naught let us say is about 100 Newton. I can straight away say my response at that specific frequency or time is about 0.1 meter. At this frequency, isn't it? Now let us compare this equation with my standard equation what I had in a single degree freedom system model. Any questions, any doubts here till? So all of you agree how did we get this equation, right, from a sample example what we are trying to do. Now I am just comparing this equation, retain this equation as it is. I will compare this equation with a standard expression is given by I am using p only to show it is a steady state response, particular integral, otherwise it is only x of t. This is equal to nothing but some value rho of cos omega t minus phi, is that right? We had this equation earlier somewhere in the first module, and we already said the rho by x static is nothing but p naught by rho by p naught k which is the amplification factor, is it not? So I can straight away say okay. Therefore, let me put it back here, x of t is nothing but d of p naught by k of cos omega t minus phi. And what is d? I will rub it here, yeah, dynamic amplification factor. I rub this, I will rewrite it. So x of t is p naught by k of root of 1 minus beta square plus 2 zeta beta square of cos omega t minus phi. Compare these two equations now. This is my equation number 13. Can you now compare 12 and 13, and can you write h omega as 1 by k of root of 1 minus beta square plus 2 zeta beta square, is it okay? This p0 by k cancels, 1 by k. Now interestingly, the transfer function h omega should also have all the components of d, is it not? It should have the components of the dynamic amplification factor what d has in the time domain, is it not? So it should qualify me, because I am now going to connect h omega with x and f omega. So now the question is, I will get the maximum amplitude, but I will not be able to capture the phase lag, okay. So I must modify x omega as I am writing this as e to the power of I phi. Now one may wonder that why I am using an exponential function here, okay. I can use cos, I can use sine, why I am using exponential? There are two explicit advantages of using this. Now d by d phi of E I phi will be I E I phi, is it not? Let us say time domain, I am talking about the time domain. Let us say d by dt of E I phi is I d by dt of E I phi, same. It means I am getting back the same function. Suppose I have got two combinations, let us say I phi 1 and I phi 2. I will again get back something of phi 1 plus phi 2, which I can say E I phi 3. Again I am getting a similar function back again, is it not? So there is an advantage that the multiplier here will not qualitatively vary your h omega, okay. So this is my transfer function. Now what is the advantage after we getting this? Very simple, I will rub this. If I know h omega, I can now straight away say one advantage is m of x is mean of this by k, and m of x is also equal to m. So, if you know the mean of my forcing function, using the transfer function I can easily find the mean of my response. Okay. Now, taking this forward, in the next lecture we will talk about how to get the response spectrum plots. Any questions here? Any doubt? Any questions? So, we started with the stationary process. We understood what a stationary process is. Then we picked up the mean and the autocorrelation function and shown that they are independent of time. So, the process remains stationary. We applied this concept on a single degree damped system for a forcing function of f0 sin cos omega t and found out the link between the response and the forcing function. We compared that with the standard expression of dynamic amplification factor. We understood that h omega contains all details of that of d, but the phase lag on the whole expression of x of t is not captured in realization of x of t in this domain. So, I have used a power exponential power here which will have a phase lag phi which will capture the quality of that content of realization of x of t on my domain. Okay. So, it amounts to a very simple expression. If I have the mean of the forcing function which is a stationary process, which is true for wave loading, I can easily find the realization of the response of the system from the load using the transfer function, which is independent of time. Okay. There is no time domain, there is no time component here at all, is it not? Phase component and of course zeta component, of course the ratio of omega and omega here, that of course anyway come in d, right. So, if I got a variance in the load, I call load spectrum. If you multiply the variance of the load spectrum with my transfer function, I will get response spectrum, which I will discuss in the next class. So, if you know the response spectrum for any given system, you can always characterize the system for any load. Therefore, we can design the system. Okay, that is what the catch is. Okay, somebody gives you a response spectrum, you want to check the system, is it safe for a specific bandwidth of omega, and the load spectrum is given to you. You can always examine the characterization of the system using only the transfer function and see what has happened to the amplification of the amplitude of the response or of the force. Okay, so it is simple. So, we stop here for this lecture.